Welcome everyone. Today I would like to talk about relativistic effects in the observed three-dimensional matter power spectrum. So my talk is based on some work in progress with Emanuele Castorina, so any feedback, any comment is going to be very welcome. Emanuele is also giving a talk, so I strongly advise you to watch our talks together since we cover topics which are related. Okay, I don't think we need a long introduction. We know that nowadays when we talk about galaxy clusterings, we mainly talk about scales around the baryonic acoustic oscillations. What you see in this plot is the matter power spectrum with data inferred from different experiments, and up to now the data which are on the left-hand side of the peak of the power spectrum can be only inferred from simple experiment. But with the next generation of survey that are going to come in the next few years, we are going to probe larger and larger volume, and so we are going to start to probe scales which are on the left-hand side of the quality scale. So we are going to start to probe scale between the quality scales and the Hubble horizon. And because of that, we need to have a correct gauge-invariant formalism to describe the larger scales. What you see now, these three different lines, is the theoretical prediction of the matter power spectrum in different gauge. So you see that this prediction, the difference between this prediction is completely negligible around the baryonic acoustic scales, but they deviate by order of magnitude once you approach the Hubble horizon. And so we see that we need to have a gauge-invariant relativistic framework to describe galaxy clusterings if you want to interpret the data coming from upcoming survey correctly at the larger scales. So roughly speaking, galaxy clustering is given by three different terms. We have the standard Newtonian picture, which combine density fluctuations and fraction spread distortions, which is good enough to describe galaxy clusterings around the baryonic acoustic scales. Then we have relativistic correction, which are suppressed by a factor h over k or h over k squared, where h is the Hubble parameter and k is the Fourier modes. These are expected to be relevant approaching the horizon. And then we might have some signature of primordial non-Gaussianity, which again they expected to have the same 1 over k squared dependence. So if you want to have a gauge-invariant relativistic description of galaxy clustering, we need to describe the quantity that we truly observe in a galaxy survey. So in a galaxy survey, we collect photons which are coming from different directions in the sky, and then we measure spectra, which give us information about the observed redshift. So the quantity that we truly observe is simply the number of galaxies in a given direction for an observed redshift. Then of course, the quantity that we are interested in is the statistical fluctuation of this number, so we need to subtract and divide by the mean of galaxy as a given direction and a given redshift. Now in linear theory, we can write the galaxy number count as a sum of different contributions that you see here. So let me just go through this equation to explain what are the different terms. So in the first line, you see the standard Newtonian terms. So you have some density fluctuation which are multiplied by some galaxy bias to relate dark matter and galaxy perturbations. Then we have redshift spread distortions. On the second line, we have the so-called lensing magnification effect. So the lensing magnification is changing the number of galaxies that we count in a given direction, simply because we might see more galaxies in a direction in the sky, not because there are more galaxies physically in that position, but because we have some magnification effect in front of them. Or the opposite situation, we may see less galaxies if you have some demagnification effect. On top of that, we have also an additional selection effect, which is given by this magnification bias parameter SB, which is modulated by the magnification effect. So in principle, in a survey, we don't observe all the galaxies, so the survey is not limited in the volume, but the survey is limited in the flux. So we can observe only galaxies which have an intrinsic luminosity above some threshold. Nevertheless, if we have some extra magnification effect in front, we might include a galaxy which in principle was too faint to be in the galaxy catalog. And the opposite is true. You might not see a galaxy because you have some demagnification effect. And then in the next line, we have the so-called Doppler effect, which is due to the peculiar motion of the source and the peculiar motion of the observer. In this R factor, you see that we have the magnification bias, we have some derivative of the Hubble parameter, and then we have this evolution bias. The evolution bias is accounting for different galaxy evolution. So in principle, we might see more galaxy at some redshift, not because of extra clustering around the redshift, but only because galaxies form with time. And so if the number of galaxies is not conserved in a common volume, you need to account for this extra term. Then we have several terms which are proportional to the gravitational potentials, and then we have terms which are proportional to the gravitational potentials, but also integrate along the line of sight, like this first term, which is the so-called time delay effect, and then the second term, which is the so-called ISW effect. Now, we have seen that we have several corrections, and up to now we didn't assume any theory of gravity to derive this equation, so the only assumption that there are behind this equation is that we have a metric theory of gravity and that the number of photons is conserved. Now we can use some Newtonian intuition to try to understand how large are these corrections. We see from Poisson equation that a Laplacian, a second derivative of a gravitational potential, is proportional to density fluctuations. And so it means that the lensing magnification, it should be more or less of the same amplitude of the density fluctuation. Of course, here we have some extra integral along the long side, some geometrical terms, but this gives us some parametrical ordering for these different effects. In the same way, we know that continuity equation is saying that a derivative of the velocity is proportional to the density fluctuation, which means that redshift space distortion should be of the same order of magnitude of density fluctuation. Then beyond this term, we have these velocity terms. Now if you compare this Doppler effect, this velocity term, with respect to redshift space distortion, you see that we have one less spatial derivative, which if you think in Fourier space, it means that this term is suppressed compared to density perturbation by a factor h, where h is the Hubble parameter over k. And so you expect this term to be important when this prefactor is order unity, which means approaching the Hubble horizon. And then we have all these relativistic corrections, which are directly proportional to the gravitational potential. And again, through Poisson equation, we know that we have a Laplacian between density fluctuation and gravitational potential. And so if you think in Fourier space, it means that all these terms are suppressed by a factor h over k squared with respect to density fluctuation. And so again, we expect them to be relevant approaching the horizon. Now we want to see what is the impact of relativistic corrections directly in terms of some three-dimensional matter power spectrum estimators. So what you see here is a so-called Yamamoto estimator, which is used to measure the power spectrum from a galaxy catalog. You may want to watch the talk of Emanuele, where it's going to give you some physical intuition behind these estimators. But let me just go briefly through the estimator. So you see that you have some density fluctuation that you are going to replace with the galaxy number count. We need to consider the survey geometry that may be non-trivial. And then when we expand the power spectrum in terms of multiple, we need to choose a line of sight. And the choice of the line of sight is going to affect the expectation values of the Yamamoto estimator. So when we have a two-point correlation function, we have two different lines of sight for the two galaxies. And then now we are required to choose a single line of sight to expand in multiple the power spectrum. So we could have different choice. We could choose the line of sight which is in between the two galaxies. We can choose the line of sight along one direction, or we can choose the line of sight, for example, defined by the bisector of the two lines of sight. Our choice is to use the so-called endpoint line of sight definitions, because we have numerical tools which are very efficient to compute the power spectrum by using this definition, because they are based on a small number of fast Fourier transforms. And of course, as you see, it's not the most symmetrical situation, but as long as we're able to treat correctly or to model correctly this definition of line of sight in our estimators, we can compare theoretical prediction, including relativistic effects, with measurement from galaxy catalog. And then, as I said, we need to replace this density fluctuation with the full relativistic galaxy number count. And then we have to include the sorbet geometry. And so you see that in real space, the sorbet geometry is just, of the window function, is just multiplied by the galaxy perturbation, which means that once we go in Fourier space, we expect to have a convolution. And so you see now that in terms of the expectation values of the Yamamoto estimator, the correlation function, the different multiple of the correlation function are coupled to the different multiple of the window function. So what you see here, this function f is the integral over the window function. And so you see that they are coupled through the 3J Wigner symbol. So in other words, if you want to compute the monopole, or the dipole, or the quadrupole of the power spectrum, they are not going to depend only on the monopole, dipole, or quadrupole of the correlation function, but you need to account for this coupling between the different multiple of the correlation function and the different multiple of the window function. Now the key quantity to compute is the full sky correlation function. Full sky because it's going to depend on the position of the two galaxies S1 and S2 and the angle between the two line of sights. So we see now that in full generality we can write this correlation function in terms of the angle transform of this double integral over the two line of sights with these differential operators which are going to act on the spherical vessel for the zero, where chi is the distance between chi1 and chi2, which are the coordinates along the line of sights. So let me just use redshift space distortion to give you an example on how we can rephrase the correlation function in terms of these differential operators. So in the case of redshift space distortion, what we have the density fluctuation, which is written in terms of some bias term, which multiplies the dark matter over density, and then we have the Kaiser redshift space distortion term. So if we compute this correlation function, we can rearrange them in this form. And now you can start to recognize what are these differential operators. So for the density part, we have just the bias, which is going to multiply the spherical vessel of order 0, while for redshift space distortion, we have the growth rate f and a second derivative, which is going to act on this spherical vessel function. And then we have the same thing for the second galaxy. And so you see that we can rearrange the correlation function in terms of this differential operator which act on the spherical vessel of order 0. Now by taking this derivative explicitly on the spherical vessel, we see that we can write the correlation function in terms of a linear combination of this generalized angle transform of the matter power spectrum. Generalized because they involve also negative power of Q. And in the case of redshift space distortion, we see that we only have two different generalized angle transforms to write the full sky correlation function. So now we have seen how we can identify this differential operator for redshift space distortion. In particular, for density perturbation, we simply have the density transfer function, which is the bias and the growth function, and then we have a delta Dirac because this, the density is evaluated only at the source position, and so this integral needs to collapse at the source position. And the same thing for the redshift space distortion, we have this delta Dirac, and then we have also, on top of the transfer function of the velocity field, we have also a radial derivative, which is going to act on the spherical vessel. Now the second derivative that you see here in orange on green is the one which is in the definition of the redshift space distortion term. Okay, so we can try to generalize this idea, including all the terms in the galaxy number counts. And here we see all the differential operators for the terms which appear in the galaxy number count. So we start from the density fluctuation and peculiar velocity that we have introduced in the previous slide. And then we need also to account for gravitational potential, velocity potential, and some of them are going to be evaluated at the source position. So we have this delta Dirac such that the integral along the line of sight is going to collapse at the source position. Some other perturbations are evaluated at the observer position. So we have this different delta Dirac such that the integral collapse at the observer position, and then we have also some terms which are evaluated along the line of sight. At this point, we know how to write the correlation function in terms of these differential operators, including all the relativistic effects. Now, by acting with these differential operators directly on the spherical Bessel function, we can find that the correlation function is written as a linear combination of this generalized Hankel transform of the matter power spectrum. Now, the situation is not as simple as the case of redshift space distortion because we have terms with different origin, and in particular, the argument of this generalized Hankel transform is not going to be always the pair separation. So we are going to have terms like we showed before for redshift space distortion, where the argument is going to be the pair separations, but then we have also terms which are integrated along the line of sight, where the argument is going to be the distance between one coordinate along the line of sight and the other galaxy, and of course the symmetric situation. And then we have situation where we are going to correlate to different coordinates along the line of sight. Then, since we have also term evaluated at the observer position in the galaxy number count, when we compute the correlation function, we have also terms which are the correlation between source term and observer term. And in this case, the argument of this generalized Hankel transform is going to be the coordinate of these two positions, S1 or S2. Or in case of terms which are integrated along the line of sight, it's going to be the coordinate Chi1 or Chi2 along the line of sight. And then we have also term evaluated only at the observer position, and in this case we have the variance of the power spectrum suppressed by negative power of Q. And finally, we have all the ingredients to compute the expectation values of the different multiple of the power spectrum estimator. Again, for simplicity, we start from redshift space distortion. So in this case, we need to consider the full-scale redshift space distortion correlation function that we have computed in the previous slides. And once we have this correlation function, we need to compute the different multiples with respect to the endpoint line of sight definition that we have adopted. And so we need also to perform a change of coordinate. We're going to replace S2 as a function of S1, S, and mu, and the same thing for cos theta, need to be replaced as a function of mu, S, and S1. Okay, then by performing these numerical integrals, we can find the different expectation values of the different multiples. So what you see here is the case of the monopole on the top line and the quadrupole on the bottom. So we consider 4 different window functions. All of them, they cover 1/3 of the sky, but they go to different redshifts. So the first one is going to 0.05 to 0.2, then we have 0.5 to 1, 1 to 2, and 1 to 4. Then the vertical line that you see in these plots correspond to the larger pair separation within this window of geometry, while the different colors represent the theoretical power spectrum evaluated at the effective redshift, which is the dashed black line. Then with the dotted red line, we have the full power spectrum, including the window function. And then the blue line, it's also considering the integral constraints. So integral constraints is the fact that in a real surveys, you need to measure also the mean density directly within the volume of the survey. And so once you are integrating to larger scales, you are going to suppress all the power. So that's why you see the blue line, which is going to drop once you go to larger scale compared to the window survey. Now we see that comparing the theoretical power spectrum with the expectation value of the Yamamoto estimator at the larger scales, the two are different. And they might be different due to different effects. First of all, we include all the wide angle effects, we include the evolution effect, and we include, of course, the convolution with our window survey in our power spectrum estimator. So all of them can be the origin of this difference, and you may want to watch the talk of Emanuele, where it's going to analyze in details the impact of these different effects and the impact on the different approximations that we normally use in data analysis. And now after redshift space distortion, we can include all the terms in the galaxy number count, so we include all the relativistic effects. The only difference is that we have to replace the correlation function that we have used for redshift space distortion with the full correlation function, including all the relativistic effects. But before doing that explicitly, let's have a look at the galaxy number counts and all the relativistic effects. Now we are in particular interested in the terms which are proportional to the gravitational potential, so the terms which are in orange here. So these terms, if you compare them to density fluctuation, they are suppressed by a factor h over k squared. So if you want to compute the correlation function phi, phi is the gravitational potential, you end up with some integral of the matter power spectrum times the Bessel function suppressed by a factor q to the 4. Now in lambda CDM, this integral is going to diverge in the infrared. So in order to get a finite result, we need to introduce a cutoff in the infrared. But then the final result is going to depend as well on this cutoff, and this seems to be a bit unnatural. Our solution to get rid of this problem is to replace this generalized Hankel transform, where we replace the spherical Bessel with the spherical Bessel minus 1. So this new integral that we use to replace the one which diverges is going to converge in the infrared. So of course you might say that we didn't solve any problem because we just need now to add an extra term. This is true. So our approach is to replace this Hankel transform which doesn't converge with the one which converge, and then we add an extra term. But this extra term is simply the variance of the correlation function. So we are going to write the correlation function which seems to diverge in terms of a correlation function which we know that is converging plus the divergence of the correlation function. And of course we sum over all these terms that you see in this orange box. Now by writing the correlation function as a sum of a term that we know is going to converge in the infrared plus the variance, we just need to study how the variance is going to behave in the infrared limit. And so we can use the result of the paper of Nastasia, Fulve and Jayul, where they show that once you include all the terms in the galaxy number count, so the term at the observer position and the term at the source position, you are going to find that the divergent part of the variance is going to cancel out exactly. Here I don't want to repeat the same calculations, but I think that we might learn something by looking at this cancellation, and this cancellation needs to be true independently from the values of magnification bias, evolution bias, and galaxy bias. We might try to look to a simpler subsample of terms in this galaxy number count to have a much simpler understanding of this cancellation. So our choice is to use the terms which are proportional to the evolution bias, and we know that since galaxy bias, evolution bias, and magnification bias are a sort of free parameters, all this subsample of the galaxy number count need to cancel themselves independently. And so if you look only at this term, you have only this line, so a much simpler subsample of the full galaxy number count. Again, we can compute the correlation function, write them always in terms of these differential operators, and then the condition that we need to find in order to have this cancellation is the fact that the limit of this function for q going to 0 has to be 0. And so this limit is going to imply the second equation, where we have a combination of the transfer function of the velocity potential and the transfer function of the gravitational potential evaluated at the source and at the observer positions, plus an integral along the line of sight, and all of this combination has to go to 0. Now we can perform the integral over the line of sight, and we end up with a simpler relation between the transfer function of the gravitational potential and the transfer function of the velocity potential. And finally, by writing this expression directly in terms of the metric perturbation and the peculiar velocity, you might recognize that this combination is nothing else than the curvature perturbation in comoving gauge. And we know that in GR, the curvature perturbation is conserved on super Hubble scales for adiabatic perturbation. So here we see that our Einstein equation, thanks to the existence of the Weinberg adiabatic modes, are going to lead to this cancellation. And finally, after having understood what is the physical origin of this cancellation, at the 1-point level, we want to understand what are the implications for the power spectrum. So far we have seen that thanks to this cancellation, we can compute the correlation function without any infrared divergences, so without requiring any infrared cutoff. But now what we want to understand is what happened for the power spectrum. In particular, we want to see if relativistic effects are going to introduce in the power spectrum some terms which are suppressed by some negative power of k at the larger scales. And of course now we have built all the machinery to test this hypothesis, but before let me go through a simple example, to a simple explanation. So let's just consider this Hankel transform that we've seen that is going to diverge in the infrared, and we have seen that we can rewrite this part in terms of some infrared safe integral plus the variance. Now for the two-point correlation function of relativistic effects, once you combine all the relativistic effects, the prefactor in front of this variance is going to be 0, and it allows to compute the correlation function correctly. Now for the power spectrum, we want to compare the power spectrum of the integral which diverge compared to the one which is safe in the infrared. In other words, we want to see what is the impact of a statement on the one-point function directly on the power spectrum. So we can take the Fourier transform of the integral which diverged in the infrared, and as long as we know how to deal with this integral in terms of distribution, we can compute them analytically, even if they diverge in the infrared. And so we find, after a short calculation, that this power spectrum scale like the matte power spectrum over k to the 4, which is the scaling independence that we expect a priori. And then for the second case, we take the Fourier transform of the integral which is safe in the infrared, and so we have this extra minus 1 term. So the term which is proportional to the spherical vessel is going to give you the same result of the previous calculation, so the matte power spectrum of k to the 4, and then we have this extra integral that you see in green. So this extra integral is just a signature of the variance in the power spectrum. And we can show that for any mode different from 0, this extra integral is exactly 0, which means that we find that the Fourier transform of these two functions are the same for any mode which is different from 0. So if you think now what is the implication of this result in terms of a real survey, we're going to expect that relativistic effects are going to scale with some negative power inside of the volume of the survey, independently of any cancellation that we might have at the 1-point level. And here you see the final results of our work, so you see the monopole and the quadrupole of the power spectrum, including all the relativistic effects for different window functions. So you see clearly that inside of the survey volume, all the relativistic effects are suppressed by some power of k with respect to the power spectrum of redshift space distortion. So you see that relativistic effects are growing, going to larger scales until they reach the boundary of the window function, and then the integral constraints is going to reduce the power at scale larger than the window function. But let's now focus on just two configurations. So let's look at the configuration at very low redshift and the very large configuration from redshift 1 to redshift 4. And so by looking at these two configurations, we see that all relativistic effects have a well-defined scale dependence with k, except the magenta line, which is referring to the correlation involving the observer velocity. So in this case, we have correlation between the observer velocity and some quantity evaluated at the source position. And so the correlation function is going to be defined by the spherical vessel of order 1 of the, not of the pair separation, but of the distance between the source and the observer. So then if you want to compute the monopole, in this case of the power spectrum, as a function of k, where k is the Fourier conjugate variable of the pair separation, you end up with these two different Bessel functions, which one is as a function of the pair separation and the other one as a function of the distance between the source and the observer. And so you don't get any specific power law because of that, but what you find is that you get some modulation, some oscillations which are modulated by this spherical Bessel function. And these are going to peak strongly at the largest possible scale, which is set by the boundary of the window function. So this is what you see. You see that you have a peak, a strong peak at the boundary of the window function, and then we have some strong oscillations. And moreover, let me stress that to compute correctly the impact of the observer velocity, we need to understand as well how galaxy catalog treat the observer velocity, so in which frame and the redshift is going to be expressed. So let's forget for a moment about this term and let's look at the other terms. And for the other terms, as I said, we see clearly that they have a well-defined power law. So let's start on the left. We see that the largest contribution is given by the Doppler effect with k like the power spectrum over k2. Then we have what we call the local term, which means that these are the gravitational potential which are not integrated along the line of sight. And here we see that again the scale like the power spectrum over k2. And so we see that this correlation is going to be dominated by some correlation between gravitational potential and the density fluctuations. Then we have that the lensing effect, if you just look at the small window function, is suppressed compared to other effects. And then the other integrated term like ISW and time delay are even more suppressed. Here you see that they have a different power law, the scale like the power spectrum over k3, and probably because these terms are integrated along the line of sight, so the physical correlation is set by the distance between different points along this line of sight and not by the pair separation. So we might change what we could naively expect in flat sky approximation. Then if you move to the second plot on the right, we see that again we have some well-defined power law. In the case of the local gravitational potential, we see clearly that the scale dependence is set by the matte power spectrum over k2. This is exactly what you expect also in flat sky approximations. Then we see that for the Doppler and the other integrated term, the scale dependence is roughly suppressed by k to 2.5, and here we might have different effects which change slightly this dependence. As I said, some of these terms are integrated along the line of sight, and then we are also accounting for a wide angle and evolution effects which might change our intuition that we have in flat sky approximation. Then if you look at the red line, which is the lensing, we see that this is the largest contribution when we look at the very large window function. And in particular, if you compare at the full power spectrum compared to redshift distortion, you see that the lensing are going to make a difference at the larger scales that you can see directly in this log-log scale. But if you want to try to understand the shape of this lensing term, you see that on small scale it's roughly the power spectrum suppressed by k to the power 1.5. However, if you look at larger scale, you see that this power spectrum deviates quite soon from this power law. And actually, if you think about what is lensing going to measure, the lensing is going to be an estimator, if you want, of the dark matter along the line of sight. In particular, it's an estimator of the dark matter with some geometrical prefactor which peak at the center between the observer and the source. And so we might imagine that when we measure the lensing contribution, what we are going to measure at the end is the matter distribution around some smaller redshift. But however, the k variable is associated to the pair separation, which is much larger than the physical correlation which is inducing the lensing effect. So it's like shifting the power spectrum on the left, and if you try to do it, if you try to shift the power spectrum, you see that you are going to reproduce quite well the lensing contribution. It is the dotted dash line. But independently of the exact scale dependence of all these effects, we see again that all of these scale dependence are growing, and it's only when we reach the boundary of the window function that the integral constraints is reducing the power of all these effects. Okay, so now we get to the conclusions of my talk. So we have seen that we have developed the formalism to include in the power spectrum estimator all the relativistic effects, which mean the effects which are evaluated at the source position, the effects which are evaluated at the observer, and the effect integrated along the line of sight. On top of that, we have included all the wide angle effects non-perturbatively in the ratio between the pair separation and the distance of the galaxies. We have included as well all the possible evolution effects, which might be important for survey which go deep in redshift. And let me stress that all these effects are relevant at a larger scale. So if you want to try to understand galaxy clustering at the larger scales, you need to include all of them at the same time. We have seen that we can use the infrared cancellation in the variance that has been shown by Nastasia, Fulvio, and Jayul to compute efficiently the two-point correlation function without requiring any infrared cutoff. And then we have confirmed that relativistic effects scale like the matte power spectrum over some power of k inside of the survey volume. And because of that, we expect that we should have, or we might have, some degeneracy to some extent with the signature of primordial non-Gaussianity in galaxy survey.